In this video, we will discuss what is a linear combination of set of vectors and the similar definition of uh, the basic linear algebra. So first we will discuss linear combination of set of vectors. What is linear combination? Let V over F be a vector space. We have a vector space. Now we call, so let v1 to vm be arbitrarily vectors of vector space V. Obviously it is over field F. So we have taken v1 to vm arbitrary vectors. So linear combination LC, we call it LC in short form, linear combination of v1 to vm is alpha 1 v1 plus alpha 2 v2 plus plus alpha m vm. It is the linear combination of v1 to vm, where alpha 1 to alpha m are in from field F. Okay, so whenever we have given some vectors, then we form a linear combination alpha 1 v1 plus alpha 2 v2 plus alpha m vm, where alpha i's are from the field and v1 v2 vm are the vectors from the vector space V. This is a linear combination of vector space. Okay, so now we will define linear span or a spanning set. Let S is a subset of vector space Bf. We have a subset. So what is the linear span or a spanning set? So linear span is denoted by L of S, or it is denoted by this symbol, and this is equal to the all set of all. We can write set of all linear combination of vectors of S, of vectors of S. Okay, so assume we have S have v1 to vm. Then what will be the span, linear span of S? This will be alpha 1 v1 plus plus alpha m vm, where alpha i's will be from field I vary from 1 to m. Okay, so this is the linear span of set S. Okay, some result. So whenever S is a subset of B, S is a subset of B, where VF is a vector space, then linear span is always a subspace. This is a notation for subspace. So linear span of S is a subspace of B, called subspace generated by set S. Okay, so we will prove this. We have L of S. What? This is a alpha 1 v1 plus plus alpha m vm, and alpha i's are from the field, or all I vary from 1 to m. Okay, we can write this 1 to m. So this is L of s. Now we have to show this is a vector space. So we can use test. So take any two element from L of s. Let x comma y belonging to L of s. What does mean it? So x will be alpha 1 v1 plus dot 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 alpha m m. We can write s. Okay, here s1 dot 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 to sm, where s is belongs to s, and y will be alpha 1 dash s1 dash plus dot 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 plus alpha n dash sn dash. Okay, so sj dash also in s. Okay, now okay, it can alpha 1 or alpha 1 dash may be same or different. Si or sj dash may be same, or it can be different also. So take any element and we have to take what? Alpha comma beta belongs to field, or to show what is to show alpha x plus beta y belongs to L of s. We need to show this one. Okay, uh, I erase this statement. I will write uh, again. So we need to show this statement. So if we write this alpha and value of x, what is the value of x? This one. So it will be alpha 1 s1 plus dot 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 alpha m sm plus beta and value of y. What is the value of y? Alpha 1 dash s1 dash plus dot 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 alpha n dash sn dash. Okay, and yeah, here j will be from 1 to n and I will be from 1 to m. Okay, so it what will be? It will be alpha alpha 1 s1 plus dot dot alpha alpha m sm plus, if we multiply this beta, alpha 1 dash s1 dash plus dot 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 alpha n, this will be beta dash sn dash. Now if we see s1 belongs to s, sm belongs to s, uh, s1 dash belonging to s set s, sn dash also belonging to set s, and this term alpha belonging to field, alpha 1 is also belonging to field, and field is closed under multiplication. So alpha 1 dash alpha 1 will also belong into field. Similarly, this will also belong into field, this will also belong into field. So if we see all the coefficient belonging to field and all the vectors are in from S, so this is the element of L of S. Because how we define the element of L of S? Element of L of S is a linear combination of element of S, where alpha 1 dot dot alpha m are in from the field F. So this will belong into L of S. This will imply L of S is a vector space. Okay, here we need to think what will be the linear combination when S is infinite. So we always take finite linear combination for a spanning of a set. We always take finite linear combination. If we have S equal to x1 dot dot to xm dot dot, these are the vector infinite vector space. So L of S will be only the finite linear combinations. We will not take infinite. Here we will take only finite linear combination. Okay. Now we also define here. This is definition or nothing else. So L of phi, okay, linear combination of this set is zero vector because there is no element in empty set. Okay, sorry, this will not be there. Okay, linear combination of phi will be zero vector because if we have any element we can define this like this, because if we have any element in the set then their linear combination will not be zero vector space. So we can define a linear span of empty set is zero vector space. Okay, now okay, the result I have erased will be proved in after proving these results. Okay, so if A is a subset of B and B and both is a subset of vector space PF, so we have to prove linear span of A will be contained in linear span of B. This is also a vector space, we have proved here. This is also a vector subspace. This is also vector subspace, not a vector space. It is itself a vector space, no dot. Okay, so take any element of L of A and so it is an L of B. It is easy to prove. Okay, I think you people will be prove. Otherwise, I will prove in the any next lecture. Okay, this is also very easy to prove. To show what is to show. So L of A contained in L of A and L of A contained in L of A. This is these both statement we have to prove. But this can be also be proved in a very efficient manner. So now I will define what is linearly independent set of vectors. Okay, first we will define when S is finite set. X, let's v1 dot 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 to vm are the element of set S and we call it independent vectors if c1 v1 plus cm vm equal to 0, and this will be 0 will imply c1 equal to cm equal to 0 means all are zeros, means all coefficient has to be 0 for c1 v1 plus dot dot cm vm equal to 0. All coefficient of the vectors has to be 0 vectors. Then we call these vectors v1 v2 vm are the linearly independent vectors. Okay, so what will be the linearly dependent vectors for okay, v1 dot 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 to vm are linearly independent if c1 v1 plus dot dot cm vm will be 0 for some ci is non-zero. Okay, here all the ci's are non-zeros, but here some ci at least one. It may be the case that we can have more than one non-zero vectors, but at least one ci has to be non-zero, and their linear combination we have defined what is the linear combination. Their linear combination has to be 0. Then we call v1 v2 vm are linearly dependent vectors. Okay, so we can take an example of linearly independent on the linearly independent and linearly dependent. Okay, you should prove that what was the result I have erased. Okay, the result was x union y. X comma y is a subset of vector space V. So a span of this set is equal to a span of this set plus a span of this set. We can prove this by showing this is a subset of first is a subset of second and second is a subset of